Imagine trying to map the structure of the entire internet using like a basic Excel spreadsheet.
Oh, good luck with that.
Right. Or trying to plot the cascading logic of the neural networks inside a large language model using those familiar, perfectly aligned rows and columns. You can't do it.
No, you really can't. A standard data matrix assumes that every single row, like every entity, is totally independent from the one below it.
Yeah, it assumes isolated data points. But in complex systems, the isolated data points don't actually matter. I mean, the only thing that matters is the invisible webbing connecting it all together. The relationships define the system.
Which is, honestly, the fundamental crisis of standard linear algebra when we apply it to the modern world. Standard matrices just collapse completely when the connections hold the actual meaning.
So welcome to today's deep dive. We are exploring a really fascinating slide deck today titled Architectures of Abstraction, Modeling the World Beyond the Data Matrix.
It's quite a title, yeah.
It is, and our mission for you today is to unpack 3 advanced machine learning architectures that have figured out how to solve this exact problem. We are going to look at similarity matrices, graph matrices, and computational graphs.
And, we are going to be getting into some intense mathematical concepts today.
We definitely are, but I promise you, the core ideas here are just incredibly clever ways to map out how different things in our universe interact.
Exactly, because the goal of all 3 of these architectures is to push past the limits of a simple grid. They model relational geometry, structural topology, and functional dependencies.
Right.
And understanding how they work, well, it gives us a window into how artificial intelligence actually perceives reality.
Okay, so let's unpack this. We are going to start with our first architecture, which is similarity matrices.
Right, the geometric approach.
Yes, so a standard matrix relies on absolute coordinates. It works great if you are plotting, like height and weight. But what if you are trying to map things that don't have physical coordinates?
Like subjective concepts.
Exactly. Say you are trying to plot highly subjective things, like how similar 2 movies are, or the vibe of a piece of music. There is no absolute X and Y coordinate for a cinematic vibe.
No, there isn't.
A standard matrix is totally useless here. So how does a similarity matrix handle that mathematically? Because the deck mentions reconstructing data through a matrix of pairwise dot products.
Right, so when multidimensional coordinates are unavailable to us, we basically have to change our perspective. A dot product is essentially an operation that takes 2 vectors.
Like 2 arrays of numbers representing our data.
Yes, exactly. It takes those 2 vectors and multiplies them to see how much they align.
So if I'm reading this right, a dot product is basically an overlap score.
That's a great way to put it, yeah.
Like if you and I both like the same 5 obscure sci-fi movies, our dot product, our overlap score is very high.
Correct.
And if we both absolutely hate the same 5 romantic comedies, our score is actually still high, right?
Yeah.
Because our tastes overlap in what we reject.
That is exactly how it works. It calculates a mathematical footprint of alignment. Now, a similarity matrix simply takes a data set and calculates that exact overlap score for every single pair of entities within it.
Okay.
It acts as a mathematical mirror. It contains the exact same geometric information as the original data, but it shifts the paradigm.
How so?
Well, instead of locating an object by where it sits on an absolute map, it defines the object entirely by how similar or dissimilar it is to its peers.
I love that. It's not, where are you? It's who are you most like?
Exactly.
And here's where it gets really interesting, especially looking at the visuals in these sources. There's this one image explaining something called the kernel trick.
Ah, yeah. The kernel trick is fascinating.
It really is. It shows a 2D graph with dots arranged in 2 flat concentric circles. There's a blue cluster in the middle surrounded by a ring of orange dots.
Right, like a bullseye.
Like a bullseye, yeah. And on a flat piece of paper, you cannot draw a single straight line to separate the blue dots from the orange dots. They are totally entangled.
They're inseparable in that dimension.
But then the image shows this mathematical expansion, and suddenly those flat dots pop up into a 3D shape that looks like a bowl. And in 3D, you can just slide a flat piece of glass right through the middle, cleanly separating the bottom of the bowl from the rim.
Yeah, that visual is perfect. By applying nonlinear transformations directly to a similarity matrix, we project data into hidden, higher dimensional spaces.
And that's the kernel trick.
That is the kernel trick. In that flat 2D space, the classes were complex and inseparable. But by unfolding those hidden dimensions mathematically, we push the data into a geometric shape where a flat linear hyperplane can easily slice the categories apart.
It's wild.
It allows machine learning models to solve complex classifications without needing to understand the raw features themselves.
It's like mathematical magic. You can't solve the problem on a flat piece of paper, so you fold the paper into a 3D shape and slice it there.
Basically, yes.
But wait, I want to push back on this because the sources highlight a massive problem with this exact
It's
process.
the scaling issue.
Yeah, the scaling issue. If the kernel trick pushes data into 3D, 4D, or even infinite dimensions to find a clean slice, and you are comparing every single point to every other point, wouldn't a computer just instantly melt down trying to calculate infinite math?
Oh, it absolutely would.
Because the slide notes that a full similarity matrix scales quadratically, meaning a dataset with 100 million points requires calculating an almost incomprehensible number of relationships.
Right. The storage alone would be something like 80,000 terabytes.
80,000 terabytes. That is computationally impossible for almost anyone. So how is this actually usable?
Well, it would crash any standard system if we tried to compute the full matrix. If you try to calculate the exact distance between every single grain of sand on a beach to every other grain simultaneously, the hardware fails.
Obviously.
So this is where the Representer Theorem blueprint comes in.
Yeah.
Machine learning models do not actually need to process the entire similarity space to understand the geometry of the data.
Okay, so how do they shortcut it?
They weigh relationships against a very specific subset of key representative data points.
Okay.
Think of it like navigating a massive city. You do not need to know the exact distance between every single house in the city to find your way around. You only need to know your distance to a few major landmarks.
Like a prominent skyscraper or a bridge or a central park.
Exactly.
So the model picks a few anchor points, the landmarks, and maps everything else relative to those.
Yes. You calculate kernel evaluations against those chosen landmarks, and you combine those with learned weights.
Oh, I see.
By doing this, you capture the vast majority of the geometric information, but you shrink that impossible 80,000 terabyte matrix down to a highly manageable 80 gigabytes.
Wow, from 80,000 terabytes to 80 gigs.
Right. It retains the structural integrity of the relationships without the impossible computational burden.
That makes a lot of sense. So similarity matrices are brilliant for abstract comparisons, mapping out vibes and subjective distances.
They are.
But that brings us to a major limitation, and the second architecture in our deep dive. What happens when things aren't just conceptually similar, but literally physically wired together?
Right, because a similarity matrix cannot read a physical cable or a digital hyperlink.
Exactly. We are moving from relational geometry to network topology. We are talking about graph matrices.
Yes. In a network topology, the assumption that data points are independent is explicitly rejected. Data here is connected via physical or virtual links.
Like a power grid.
A power grid, a subway system, or the global internet. Proximity is no longer measured by geometric distance or conceptual overlap.
Right, because two people could live in the exact same apartment building, which is geometric proximity, but have totally different friend groups.
Exactly.
In a network, proximity is purely about who you are linked to. It is measured by path traversal, which conceptually makes sense, but it brings up a really practical question about translation.
What do you mean?
Well, we can look at a visual web of nodes and lines and intuitively understand the clusters. But a computer cannot see a drawing of a social network. How do we feed the physical structure of a web into a machine learning algorithm?
Okay. We use what the sources call a translation engine, specifically the graph Laplacian.
The graph Laplacian.
Yes. The mathematical shorthand in the deck is L equals D minus A. The goal is to translate that physical graph topology into linear algebra.
Okay, rather than just reading the letters, let's break down the logic of that equation. What are the D and the A actually doing?
Let's start with A. A stands for the adjacency matrix. Imagine a giant grid where every row and column is a node in the network.
Okay.
If two nodes are directly touching, say, two web pages linking to each other, you put a 1 in that box. If they aren't touching, you put a 0. It is just a raw, unweighted map of neighbors.
Got it. Just a giant grid of yes or no questions. Are we touching? And what about the D?
D is the degree matrix. This is much simpler. It is just a tally of how many total connections a single node has.
Oh.
So a highly connected influencer has a massive number. An isolated user has a small number. Now, the graph Laplacian, the L, is created when you take that degree tally and subtract the adjacency map.
Wait, so you take the total number of connections a node has and you subtract the actual map of its neighbors. What does subtracting them actually achieve?
What you are left with is a mathematical footprint of a node's isolation or integration.
Oh, interesting.
By subtracting the specific links from the total volume of links, the resulting matrix captures the structural energy of the entire network.
Structural energy.
Yeah, it creates a system of equations that acts almost like a series of springs connecting the nodes, mapping out the tension and flow of the entire web.
And once it is in that mathematical format, once we have the tension of the web mapped out as numbers, the sources say we can perform eigendecomposition.
Yes, eigendecomposition.
The deck calls eigenvectors the fundamental energetic components of the matrix, which, I mean, sounds like poetry, but what actually is an eigenvector in this context?
Think of striking a large bell. The bell is a complex physical object, but when struck, it vibrates at very specific natural resonant frequencies. Eigenvectors are the mathematical equivalent of those resonant frequencies.
Oh, I see.
By decomposing the graph Laplacian matrix into its eigenvectors, we reveal the hidden macrostructures of the network. We see the natural frequencies of how data or influence flows through the connections.
Let's tie this to the real-world applications mentioned in the deck, because this is where the theory turns into massive industries. The sources highlight spectral clustering and PageRank.
Two incredibly important algorithms.
Yeah, and spectral clustering relies on the right eigenvectors of the graph Laplacian.
Yes, spectral clustering uses those right eigenvectors to find community cuts. It looks at the resonant frequencies of the matrix and identifies the natural fault lines in the network.
Fault lines.
Right. It calculates exactly where a giant web naturally wants to break apart into distinct subgroups.
Like looking at the massive web of who texts who in a high school and having the math automatically draw circles around the distinct friend cliques, even if no one explicitly labeled them.
That's a perfect analogy.
Yeah.
It finds the underlying structure through the math. PageRank, on the other hand, which famously revolutionized search engines, uses a different approach. The sources note it uses the left eigenvectors of what we call a transition matrix.
Wait, why the left? What is the difference in what it is searching for?
Well, if the right eigenvectors are finding the fault lines to cut the network apart, the left eigenvectors are tracking the flow of traffic over time to find node prestige.
Node prestige.
Yeah. Imagine dropping 1 million random wanderers into a massive maze of hyperlinks. They click links totally at random. Over a long enough timeline, where do they end up most often?
I mean, they are going to naturally funnel toward the nodes that have the most pathways leading to them.
Exactly. The central, highly linked nodes act like gravity wells. PageRank uses those left eigenvectors to calculate that theoretical flow, allowing it to mathematically rank the prestige and central importance of every single entity in the web.
Finding the center of gravity of the internet using linear algebra, that is just fascinating.
It really is.
And that brings us to the third and final architecture, computational graphs. This is a massive thematic transition.
Very much so.
First, we looked at nodes as abstract data points comparing subjective similarities. Then we looked at nodes as physical entities connected by wires or links. Now we are looking at what happens when the nodes are the mathematical operations themselves.
Right, and this is the foundation of deep neural networks.
Okay.
Often, a function is so impossibly complex, like recognizing a human face in a blurry photo, that it simply cannot be expressed in a single closed-form equation. You cannot just write y equals mx plus b for a human face.
Definitely not.
When a function is that complex, it must be modeled as a computational network, specifically a directed acyclic graph, or a DAG.
Let's define DAG for a second. Directed means the data flows in one specific direction, and acyclic means there are no loops. Like you can't send data backward to a previous step in the middle of the process.
Correct. The variables in the mathematical operations themselves become the nodes of the graph. The edges are the pathways the data takes between those operations.
You know, the classic analogy here is usually a factory assembly line, but honestly, that feels a bit too rigid for what the sources describe.
I agree.
It feels more like tuning a massive, unbelievably complex instrument. You have data flowing through these operational nodes. Maybe one node squares a number, another applies a specific algorithmic filter, and the system is trying to output a perfect chord.
I like that analogy.
And what makes this work is the dual flow of dynamic optimization. Backpropagation, it happens in 2 phases.
Yes. The first phase is the forward pass. The data flows through the mathematical nodes, computing an initial prediction. But crucially, as it moves forward, the system caches the local derivatives.
Caches them.
It remembers the exact rate of change at every single operational step. It records how much each specific node contributed to the final outcome.
And then it checks that final outcome against the correct answer to find the error, the loss. It realizes the chord is out of tune.
Right.
And this is where it throws it in reverse for the backward pass.
Exactly. During the backward pass,
Mhm.
it utilizes the chain rule from calculus. Because it cached all those local derivatives, it can multiply them backward along the exact same pathways. It distributes the error gradient across all the learned weights in the network.
So it's like hearing that out-of-tune chord, and instead of just guessing what went wrong, you mathematically trace the discordant sound backward through the instrument.
Precisely.
You know exactly which string needs to be tightened by exactly a fraction of a millimeter to make the chord resonate perfectly next time.
That's backpropagation in a nutshell.
But I have to push back here, because the visuals for basic computational graphs often show single numbers flowing through these nodes, a 1 passing to a 3. Doing basic calculus on billions of single isolated numbers one at a time sounds incredibly inefficient.
It would be, which is why modern neural networks require vector-centric upgrades. Modern networks absolutely do not pass single numbers.
That's okay.
They pass high-dimensional vectors and matrices through linear transformations. The standard scalar chain rule we all learned in high school calculus, which deals with single variables, has to be entirely upgraded to handle this. Vector-to-vector derivatives are calculated using transposed Jacobian matrices.
Okay, transposed Jacobian matrices is a heavy phrase. I mean, the deck introduces it, but what is a Jacobian matrix actually doing functionally?
Well, if a standard derivative tells you the rate of change for one variable, a Jacobian matrix is a massive grid that maps out the rate of change for thousands of variables all at the exact same time.
Oh, wow.
Imagine a soundboard with 10,000 sliders. Turning one slider slightly might inadvertently change the output of 500 other sliders.
Yeah.
The Jacobian matrix maps all of those interconnected simultaneous relationships.
So instead of tuning one string at a time, you are dynamically tuning the entire orchestra at once, mapping how every single instrument affects the others in real time.
Exactly.
And this matrix approach to calculus is what enables massive parallel computation, right? It's how these networks can process millions of images in hours.
Without the Jacobian matrices handling those multidimensional derivatives, modern deep learning would simply not exist. It handles the cascading logic at scale.
So what does this all mean? We have explored 3 very different domains today. We talked about relational geometry unfolding hidden dimensions with similarity matrices and the kernel trick. We talked about structural topologies, translating physical webs into math with the graph Laplacian to find prestige. And we just talked about functional dependencies, mapping the flow of calculus through a network using Jacobian matrices. Conceptually, they feel like totally different disciplines.
On the surface, they appear completely unrelated. But this brings us to the grand synthesis of this entire deep dive.
Okay, Hibby.
Regardless of how we choose to abstract the messy, unpredictable world, whether we are mapping the subjective vibes of movies, the literal hyperlinks of the internet, or the complex mathematical flow of a neural network recognizing a face, the underlying solution methodology is identical.
I mean, let that sink in for a second. These drastically different problems, these entirely different ways of perceiving reality, all collapse into the exact same mathematical toolset.
They do. Data relationships, structural relationships, and functional relationships all rely heavily on matrix factorization and eigendecomposition.
All of them.
All of them. They all require translating a complex system into a matrix of numbers, and then factorizing those numbers to reveal the hidden architecture beneath. To summarize the central thesis of our sources, I think it is best to look at the universal blueprint provided at the very end of the text.
What does it say?
It states, no matter how complex the relationship, machine learning ultimately reduces to the elegant decomposition and traversal of matrices.
The elegant decomposition and traversal of matrices. You know, we started today talking about the limitations of that standard spreadsheet grid.
We did?
How a simple row and column setup couldn't possibly handle the intricate webbing of a complex system. But what we've discovered is that by fundamentally rethinking what a matrix can hold, by using it as a mirror for abstract similarity, a flattened mathematical footprint of a physical web, or a dynamic registry of flowing calculus, we can model almost anything.
We abstract the world into numbers. We translate the invisible connections into linear algebra, and then we factorize those numbers to find the underlying truth.
We break the standard grid, we fold data into higher dimensions to slice it cleanly, we capture the resonant frequencies of entire communities, and we upgrade calculus to tune millions of variables simultaneously.
They're all connected.
All in pursuit of finding the hidden structures that define our reality. Which leaves you with one final, lingering question to think about after we wrap up today's deep dive.
Oh, I like a good lingering question.
If every complex system in our universe, from the prestige of a single web page to the subjective similarity of two human ideas to the literal flow of dynamic logic itself, if all of it can ultimately be flattened into a matrix and factorized to find its hidden truth, what aspect of the human experience, if any, will ultimately resist being captured by this mathematical blueprint? Think about that the next time you open a spreadsheet.